In this video, we'll take a deeper dive in how we can index or select data from our series and data frames, and also how we can assign new data to them. During this video and throughout the lecture in general, you'll see a lot of new syntax. Your task is not to remember every single line of code, but just get the general idea, so that in the end you know what is possible. And so then, if you face a certain problem in the future, you know where to look up the solution. Or at least you can narrow down the space where you would search for a solution. Okay, so starting off with the Pandas index object. We can create index objects using pd.index, and we can think of that as an immutable array. So it looks like an array, it also has a d-type, but if we try assigning new values to it, we get the error that index does not support immutable operations. And once we created our index, we can pass that to the Pandas series, and then from that create a series with the according indices. We can also give a name to our index object. And then if we create a series from this named index, we get the same output except that we have now a name. The same logic applies to data frames, so now we put the data of our series into the constructor of the data frame, we pass our index to the index argument, and we also define a column name. So now our data is in the form of a data frame. Naming our indices can be useful, but it can also be a bit distracting. And so if we want to remove the name, we just write df.index.names and set that equal to none. Note the list brackets around the none. This will be relevant later when we have multiple indices. So once we set the name to none, we're just left with the column name. We started off comparing the index object to a NumPy array. And so just like a NumPy array, we also have attributes such as size, shape, dimensions, or d-type. A very important feature of the index object are set operations. So for example, we can calculate the intersection between indices. So this gives us the values that are contained in both indices. We can also calculate the union, so combining both indices, and also the exclusive OR, which gives us the elements that only appear once considering both indices. And this feature is very important for when Pandas does operations such as merging or joining data frames. So maybe we could imagine two data frames that collect information about persons, and so if our index is a unique identifier for these persons, we could then join the information with the help of these set operations. Okay, now onto data indexing, selection, and assignment. In general, we can say that all this works very similar to NumPy. So we can do normal indexing, slicing, masking, and also fancy indexing. But there are some quirks that we should be aware of. So just as a refresher, in this code cell here, we select all the rows from A, then we take the second and fourth column, and then we select from the second and fourth column again, and we use a mask that checks if the values in these columns are divisible by 3. And so that gives us then from the columns 2 and 4, the values 9, 3, and 15. And so here we have 3, 9, and 15. And all that is also possible in Pandas. So let's start with data selection from series. And we'll begin with imagining again the series as a dictionary. So that's the series we're working with. We have the explicit indices A, B, C, D, and here we have our values. And just like for dictionaries where we can check if a key is contained in a dictionary, here we can check if an index is contained in the series. And we can do that either with the contain standard function or using the in operator, which then calls this standard method. And the Pandas series object actually provides this keys method here, which is equivalent to accessing the indices. So this will return true. We can also use the .items, and just like a dictionary, this will give us the keys and the values in form of tuples. And then we can also use the key or index to access one of the elements and then assign a new value. And so since that index is not present yet in our series, it will create a new entry. So now we extend our series by this row here. Okay, next up we imagine our series as a one-dimensional array. And so if we remind ourselves of how we can access data from arrays, what comes to mind are things like slicing, masking, or fancy indexing. And so all that also works for our series. And the cool thing is that we can use the explicit indices. So we can slice from A to C. Note that C is also included. We can also still use the implicit index, so go from 0 to 2. Here the 2 will not be included, so our third element. Then we can also do masking. So here we create a mask that checks if the values are greater than 0.3, and if the values are smaller than 0.8, then also our mask is true. So it's true for the values B and C, and these values are in that range. And then we can use this mask to select the values from our series. Finally, we also have the fancy indexing, so we pass multiple indices to get the respective values. For the indexing that we've done so far, we sometimes use the implicit and sometimes the explicit index. And this didn't cause any problems yet, but things start to get confusing if we define our explicit index also with numbers. So we pass the values 1, 2, 3, 4 as an explicit index. And when we then slice our series, it will not refer to this explicit index, but to the implicit index. So we skip the first value, which corresponds to the explicit index 1, but instead we start at 0.5, which corresponds to the implicit index 1. So implicit is 0, 1, 2, 3, and so 1 starts here. We can also see this in another example. So here we have a series with the explicit index 1, 5, 3 and the values ABC. And when we use slicing, it ignores the explicit index and just uses the implicit index. So 5 and 3 of course do not relate at all to the 1 to 3. When we do normal indexing, however, then it will always refer to the explicit index. So indexing with 1 would access the second element if we were to do implicit indexing, but since we now refer to the explicit index, we don't select the second row, but the row where our index is 1. And so that gives us A. Okay, by now you should be really confused by when the explicit or implicit index is used, and this confusion will get worse once we introduce multi-indexing or once we get two-dimensional for the data frame. And to address all this confusion, what we do is we use the lock and ilock attribute. And the lock attribute will always access a location in the series using the explicit index. So this holds for normal indexing. So we get the element that corresponds to the index 1, and it also holds for slicing. So we get all the elements from the explicit indices 1 to 3, also including the 3. While coding becomes way more intuitive using the lock and ilock attributes, they can also sometimes be a little bit confusing. So here we have an index that is not monotonically increasing, so we go from 1 to 5 and then back to 3. And when we now try slicing with indices that do not exist, that throws us a key error, which is to be expected. But now when we have indices that are increasing monotonically, so 1, 3, 5, then we can try slicing with values that do not exist. So even though our indices don't go until 10, we can still slice from 3 to 10, and that gives us then all the values corresponding to indices that are equal or bigger to 3, but smaller than 10. And the slicing even works if not a single value is present in the original indices. So we try going from A to C, which are not even numbers, and that returns us just an empty series. Okay, now onto the ilock attribute, which we can use for implicit indexing. So indexing now with 1, we expect the second row, and indeed we get the value B, and slicing from 1 to 3, we go from the second to the third element. So here the 3 is exclusive again. And using lock and ilock is also supported by the Zen of Python. So there it reads, explicit is better than implicit. And note that this does not refer to indexing, but to our code style. So we want to be explicit about whether we index with implicit or explicit indices, so that we don't have to guess what index Python will use. Okay, so much for series. Now on to selecting data from data frames. And here we can also start with the syntax that relates to dictionaries. So we use a key, or in this case a column name, pass that as an index, and we get the respective column as a series. We can also use dereferencing to access the columns by just writing dot and then the name of the column, but this can lead to side effects if we have a column that is named values, because the dot values already refers to something else, namely all of the values. Or if we name a column with a uppercase T, that might also cause confusion, because the capital T will transpose our values, or the whole data frame. Okay, now let's index the data frame with both columns and rows. And we can do that by first accessing the dot values, which gives us the contents of the data frame as a numpy array, and then we can apply normal numpy indexing. But the better approach is to use the lock and ilock indexes provided by Pandas, which also allow us to index the underlying numpy array, but we also get to keep the column names and row indices. The same kind of indexing works of course also with the explicit index. And here we again use the .lock. So we get the rows from the beginning up until, and also now including the row with the index Illinois. Same for the columns. So we go from the beginning up until and also including the population column. If we want to select specific columns, we can pass these columns as a list. So here we specify area and population, pack that into a list, and we specify that we want all rows. And so we get all the rows for the columns, area and population. If we don't want all the rows but just a single row, we can also specify that row. So here we write California, giving us that row, and from that row we want all columns. And that returns us the California row as a series. Okay, so much for selecting data. Now let's create new columns. And that works just like when we created new key value pairs for dictionaries. So we access a column which does not exist yet, and then we pass it a Pandas series. And so here we divide the population column by the area column, and that will give us the values for the density. And we'll also combine it with masking. So from our data frame, we select those rows where the density is higher than 100, and from these rows we want the columns population and density. And that's what we get. Sometimes it might also happen that we want to combine explicit and implicit indices. And we can do that by chaining them. So let's first look at our data again. And so what happens here is that we use implicit indices going from 1 to 4. So we take the rows from Texas to Florida. So the implicit indices are 0, 1, 2, 3, 4. And so we skip Illinois since 4 is exclusive. So we get the rows Texas until Florida. And then from these rows, we use the explicit index to select again all the rows. So it's still Texas until Florida. And then from that, we select the columns population and density. So here we see Texas until Florida, population and density. Using these explicit attributes, we notice that the row came always first and then the columns. If we're not using ilog or log, then we can get confused by whether we refer to the columns or the rows. So in this case, we refer to the columns as we have a single index value, but then when we do slicing, we'll refer to rows. So we get the rows Florida until Illinois. And this can really be confusing. So if we try accessing the columns area until population, that does not work. So if we go back to the log attribute, it is immediately clear what's happening. We select all the rows, and then for columns, we do slicing from area until population. A small note for accessing a single value, for that the add attribute is faster. So if we're just interested in the row Florida and the value of the column population, then using .log takes 4 microseconds, while using the .add just takes around 2. Okay, next up, the probably most important image or overview of the whole notebook, because this will tell us what kind of behavior we have to expect from our indexing. So are we referencing columns or rows, or will our index be interpreted as explicit or implicit? And so let's go quickly through that. If we use the normal direct bracket access, so without the .log or .ilog, then if we have a single argument in these brackets, we refer to the column. For example, we access the area column. If our argument is not a single value but a slice, then it will refer to the rows. And having both arguments in our brackets isn't even possible. For that, we would need 2 brackets. So one for accessing, for example, the area, and then in the area column, we go from Texas until Florida. And while this looks like a viable solution, we run into problems, or at least might get confused when we pass a single index. So imagine we select the column area, and then we select the row Texas. And this works of course fine, because what this here is not actually a data frame, but a series. So this syntax with the square brackets and a single value will not access any columns because there are no columns, but we're just indexing the series. So if we would change our mind and would also now be interested in the column population, then we get an error, because now this is not a series anymore, but a data frame. And then this syntax will try to access the column Texas, but Texas is only a row. And to fix all that, we switch to the log attribute. And so we specify that we're interested in the row Texas, and we want the columns area and population. Okay, again, a single index gives column, a slice index gives row, and if we want both row and column, we already run into troubles for this direct access. And so instead, let's have a look at the log and ilog. And here a single value refers to the row. If we have a single argument, which is a slice, we also refer to the row. And if we're interested in both row and column, then we can pass first the row and then the column, either as a single index or a slice. And that all works with the explicit indices. And for the ilog, we use the implicit indices, but we have the exact same logic. So single index is row, single slice also row, and you can also combine row and then column. The only difference is that for the implicit index, the slice top is not included. So slicing from 0 to 2 will stop at the implicit index 1. Okay, next up, reindexing. Here we have a data frame that has as rows different browsers, Firefox, Chrome, so on. And in our columns, we have a HTTP status and a response time. And so what happens if we create a new row index and replace the index of our data frame with that index using the reindex function? And what we see is that the rows that appear not in this new index are gone. So Firefox is not present anymore in this new data frame. but the browsers that do appear are kept. So we have, for example, Chrome just at another position. So it's going from second to last since we specified it here in the last position. For the rows that were present in the original data frame, the values are also transferred to the new data frame. And for our new rows, for example the Komodo dragon, we didn't specify any values. And so it tells us not a number. So we don't have a value yet. The same works for columns. So we apply the reindex here not to this data frame but to this data frame. And so the HTTP status is kept. But we don't take the response time, and instead we create a new column which is called user agent. And for that column we of course also don't have values yet, and so it's all nonce. Another feature is that we can rename our columns. So here we create a data frame with the columns A and B, and before even printing our data frame we will rename the column B to C, and we can do that with a mapper that takes a dictionary where the key is the column that we want to rename and the value is the new name. And so now we have a column named C but not B. The same can also be applied to the row indices. For that we just exchange the columns with index. Okay, now on to Boolean indexing, or basically masking. So we have here data frame where we have as row indices different dates, and then the columns A to E, and these are just random values. And in our column E we have the strings 1 to 3, and then a repetition of that, so again 1 to 3. And in this cell here we create a mask based on the column A. So we compare all the values of column A with 0.5. and check if they're bigger than that. And so only this row and this row evaluate to true for that condition. And then we can use this mask for indexing and we get the two rows. There's also an alternative syntax that we can use, which is the dot query. So we pass again our condition and we get our two rows. Another way of creating a Boolean mask is the isIn function. So this will check if the values of our column E are contained in this list here. So the list containing 1 and 2. And if you remember the column E, we had the strings 1 to 3, 1 to 3, and so 1, 2 evaluate to true, but not the row containing the value 3. And so then here we apply this mask to our data frame, and now we're not just displaying these rows, but we're replacing every value of these rows where this mask is true with a none. So now the rows where our column E had the strings 1, 2 are all filled with nones. We can use the isNA function to check which of the entries in our data frame are nones. So here for whenever we have a none, it will evaluate to true in here. Sometimes we're interested if some condition applies to the whole row. So not just the individual values, but to the whole row. And so that can be checked with the .any. And we pass as an argument axis equals to 1, which indicates that we care about what happens in one row and not the column direction. So the any will check if any of the values in the respective rows are true. And so here all the values are true, and so also the result here will be true. And in that case we could also use the all instead, which checks if all the values in a row are true. And this can be then again used as a mask, because we reduce it to a single series of truth values. So if we pass it as a mask, we get the 4 rows where the mask evaluates to true. If we use the tilde operator, so this wavy line here, then we negate the mask, and so it will select the rows where this mask is not true. And so all that this code did was selecting those rows where we don't have any nones. So we started with this data frame here. We used the isNA function to check which values are nones. Then we used the .any to check if there's at least one none in a row. And then we used that mask to drop all the rows where there was at least one none. And this operation can be really useful if we don't want to deal with any missing data. And so because it is so useful, Pandas also provides us with a dedicated function for that, which is called dropNA. And here we can also specify how we want to drop the columns. So should we drop a column if any of the entries are missing, or only if all the entries are missing? And so this code is equivalent to this here, except that it's much more readable. Okay, now to an exercise for you. What you get is a data frame that has the columns name, score, attempts, and qualify, and your task is to get the names and scores of those people where the number of attempts in the examination is greater than 2. And the names and scores of these people should be in form of a dictionary. So the name should be the key and the score should be the value. Again, you'll find the solution below the video. Okay, let's continue with data assignment. So we start off with a data frame containing a single column called temperature. And just like for dictionaries, and also like we saw before, we can simply access a column that does not exist yet, pass that some value, and then we have a new column. We can also create new columns based on existing columns. And so here we're checking if the temperature of Portland and Berkeley is below or equal to 18. and we can interpret the returned truth value as telling us if it's too cold or not. So the 17 degrees Celsius in Portland is truly too cold. And so here we create a new column called too cold, and we assign it this series. So now we have the column too cold, and it's telling us that it's too cold in Portland, but not too cold in Berkeley. Note that these operations work in place. So we are directly creating a new column and assigning some value to it, and we're changing the actual data frame. If we want to do something not in place, we can use the assign. So we create again our data frame, and then we call the assign on our data frame, and as an argument we pass a new column name, and the value of the argument is here a lambda function that will go through all the temperature values and will convert them to Fahrenheit. And this operation is now not in place, but it will return a new data frame which we assign to data frame 2, and then we can print this new data frame. And there we now have the temperature column in Fahrenheit. There's also a slightly more intuitive syntax for that, which does not rely on lambda functions. So here we directly access the data frame column temperature C, do some operation with that, and then assign that to this new column. We can also do multiple assignments simultaneously. So here we create the columns temperature in Fahrenheit and also Kelvin, and if we run that, we get 2 new columns. And all these operations were not in place, so they didn't change the actual data frame, but returned a new data frame. Okay, next step, row assignment. For a single value in a row, we first index using the .log, the row, and then the respective column, and then we can assign to that spot a new value. So now we went from 25 to 26. If we want to instead change the whole series, so the whole row, then we have to replace the old series with a new series. And so we do that by first accessing the row, using again the .log and then the row name, and then we assign to that a new Pandas series. And in this series, we specify the values for the different columns. So here we just have one column, but if we had more columns, we would add more key value pairs to our dictionary. And so now the temperature in Portland is updated. Now what happens if we have rows which are not unique? So let's concatenate the same data frame twice, and then we'll try assigning to the rows Osnabrück and column temperature a new value. But now we have 2 rows with the index Osnabrück, and so what happens is that both values are changed. And what can cause problems now if we don't want to change just the value for that column, but for multiple columns. So we would pass again a series. Since we only have one column, we just have one key value pair in our dictionary. But the problem now is that dataframe.log doesn't just give us access to a series that we could overwrite, but it gives us access to a data frame. So the error message will tell us here we have some shape mismatch. And if we check out the row Osnabrück, we see that we actually have 2 rows, so a whole data frame. And of course we cannot assign to this data frame just a single series. So this series here. And so to replace one specific row with the index Osnabrück, we use the np.where. That gives us the index where our row has the name Osnabrück. And then we'll access the first element, so the first index, this 2 here, using these double zero brackets. And we have to do that because this here is a tuple. So we first take that part before the comma, and then from the array again the first element. And so this gives us the 2, and then we use the 2 as an implicit index. And we get the temperature value for our first Osnabrück. Or actually not just the value, but the whole series. So the whole row. And so with this row, we can then assign a new series to that. And that way we updated one of the Osnabrück rows. Okay, now on to multi-indexing. In Pandas, we have the option to create our index not just as a list, but here as a list of tuples. And if we just call the pandas.series constructor and pass this list of tuples as an index, then we just get single indices but as tuples. If we instead use the multi-index.fromTuples function to create our index, and then we can also give this index some name. So the first value should be state, the second one should be year, and then we can use this now called multi-index and pass it to the reindex function of our series, and this gives us then a proper multi-index, also called a hierarchical index. So on the first level we have the states, California, New York, Texas, and then for each of these indices we have a second index corresponding to the years 2000 and 2010. And we actually missed the .names here, so let's repeat that. And now we also have proper names for the indices. And to now access our values, we have to pass 2 indices. So one for state and one for year. And since we're just dealing with series, we can use the normal brackets and then pass the first index and then the second index. Of course, the implicit indices also work. So we can take the first value and also the second value. Things get really interesting when we start unstacking these indices. So let's first print the population series here. And this series already looks kind of two-dimensional because we have two indices. And this two-dimensional structure is recognized by Pandas. So if we unstack this series, we get a two-dimensional data frame. And so in the series we had two indices, and one of them will be now used for the row indices and one for the columns. So the states are the row names and the years are the column names. We can also remove the names again to make it a bit more readable. And as of now this looks a bit weird since we have the states in the rows and the years in the columns. So we can just transpose the data frame, and now we have the more common structure where the years are in the rows and the states in the columns. The same can be achieved by passing the level argument to the unstack function. So if we unstack, then it takes the first index immediately as column names and the second index as row names. And then of course we can also stack this data frame again, keeping the row names as a first index, and then as a second index we have the column names. If we want to go back to using the implicit index, we can use the reset index function. So right now we have two indices here. And if we reset the index, it will turn both of the indices into columns. And we can also pass a name for the values, which is then also turned into a column. Playing around with all these stacking, unstacking, resetting functions can be useful in the beginning to get a good grasp of our data. Feel free to play around in the notebook with all these functions to get some more intuition of how they work and what can help us better represent our data. In this video, we'll only cover two more things, namely setting an index and resetting the index. So that's the data frame we're dealing with. We have the columns state, year, and population, and then we can call on this data frame the function setIndex and pass as an argument the name of the state column. And we'll also remove the index name, and that gives us then a data frame with the states as indices. And as a general note, if we're slightly confused with these hierarchical indices, and they sometimes can look a bit confusing, we can just call the .resetIndex, and that gives us this flat structure here again.